Hello, this is QMG, transmitting more information on quantum mechanics. Well, I'm happy to say that I sent my first manuscript for publication, and here's a title: A Delayed Choice Quantum Eraser Experiment with an IBM Quantum Computer. And there's my real name. I'm not QMG. You can actually find this paper just by typing this title in Google. People from Google did a wonderful place in making sure that you can find my paper right away, right on the top. It's in several repositories. So let's begin. All right, what is a delayed choice quantum eraser, quantum experiment? Well, let's start with the general category. An experiment where the past of a quantum system can be defined in more than one way based on the way the system is measured in the present. Right? A typical question that comes to mind in a delayed choice experiments are: can future measurements change measurements in the past? Also, retrocausation. Does the act of measuring something in the future erase previous measurements in other parts of the system that were measured earlier? Okay, so I will deal with these questions, and a very interesting question that often comes to in this that often makes the delayed choice quantum eraser experiment very important is this one: retrocausation. Can future events cause something past? So let's deal with it. So let's begin with the master, which is Wheeler, right here, right next to me. So here is Wheeler's delayed choice thought experiment. So yeah, it started just with a thought that Wheeler came up with a long time ago. By the way, Wheeler was the thesis advisor of Richard Feynman, so he's a very, very intelligent guy, right? Okay, a photon from a distant source is detected in 2D. So here's a picture, what conceived. So he imagined a source right here, and as you can see, a photon can come up in two different paths. Can go into the upper path, as you can see right here, or you can go into the lower path, as you can see right here. And right here is where you and I are. We're on Earth, and we can detect the photon in two different ways, right? One way is to know which way the path went through. Did the path go through the up path, or did the photon go through the lower path, right? So that's one way of detecting the photon. And of course, if you detect the path where the photon went through, you can say the photon behaved like a particle, right? So, just like when you throw a ball, it goes one direction or the other direction, and you can just detect which way the ball goes through. But here's a weird thing, and you may not be surprised about this one already. So if you don't know which path the photon went through, you can detect an interference pattern. So it starts behaving kind of like a wave, right? And as you can see right here, you can see waves coming out of the source, and you don't know which way the waves went through, but when the photon gets here, you detect a wave pattern, right? Of course, you need a lot of photons in order to detect a wave pattern. And so it almost looks like you can determine the past of the photon based on the way you measure it in the future, right? So these can be billions of, it can be really far in the past, and billions of light years away, and we can determine the history in the past just by the way we measure it in the present. Okay. Now let's go to the next slide. So here is the lab version of that experiment, and it has been done in so many ways. You can call this one the Wheeler's delayed choice quantum experiment, and you can see right here, you can throw the photon. The photon here can go into two directions: the upper path, or the lower path, this one right here. So we can call the upper path, oops. So you can call the upper path 1, and you can call the lower path 0, right? And right here, you can decide how you're going to look at it. See, right now you have these are half silver silver plate mirrors. I believe that's the correct name for it. And this one can split it into two. You can make the photon go into two directions. And same thing right here. And as you can see, the way it is set up right now, it can go into this detector or this detector right here. Because we don't know which path the photon took, you expect to detect a wave pattern in those detectors. If we remove this yellow mirror here, we're just going to know exactly which path the photon went through. And of course, you can associate one with wave behavior and the other one with a particle behavior. So here are the results. You can find a lot of these ones online everywhere. So here's one path that you find. Here's a flat path, flat pattern, and here is the wave pattern, right? You can guess which one is which, right? So when there is no mirror, you get this pattern right here, the one in blue, right? There's no interference. But when you put the yellow mirror, you actually get this pattern right here. 4 different phase values. Let me go back a little to explain that part right there. So as you can see, this green thing right here can change the phase of the waves, right? So if you have waves, you can change the way they arrive, right? You can move them slightly forward, slightly backwards, right? Kind of like this, right? Kind of like that, right? The crest can match, or the crest can be out of phase, right? So you can vary that, and of course you're going to get a different pattern, right? Constructive, destructive interference pattern. And that's exactly what you observe right here for different phase values, right? So as you can see in the lab, you can also change the path of a system based on the way you measure it in the future, right? And you can say that's kind of weird, yeah, but all right, we'll get to it. I'll get to my experiment right in a second. So here's the quantum computer equivalent of Wheeler's delayed choice quantum experiment. Now that you have quantum computers online, anybody can just start doing all kinds of experiments. And here is somebody already published a paper like this paper right here. You can actually find it in the archives. I will show you the citation for this paper. So right here is the circuit, as you can see. All right, so you can imagine the top part is both paths, right? So this right here, you can imagine that you start with a qubit here, and it can become, this one goes through the upper and lower part at some point around here. And this one right here, the purple one, is activated by this one below, okay? And then you measure the results, okay? I'll explain it a little bit more. I know it's kind of hard to, to see how this one exactly is just like the other one. So when CH is activated, a wave pattern is formed at Q0. So right here, we're going to detect a wave pattern when this purple gate is activated. And when CH is not activated, a particle behavior is formed at Q0. So right here, we're going to obtain a particle behavior. And CH is controlled by a U3 gate at Q1. So either set at 0 radians or pi over 2. So right here, as you can see, you can actually set it as 0 radians or pi over 2. This is the equivalent of putting the yellow mirror, or taking away the yellow mirror, okay? So the upper and lower paths for Wheeler's experiment are basically formed right here on this right here. Okay, kind of hard hard to see, but well, that's how you can actually do it in a quantum computer. And if you go into the if you plot the results for different phase values, you get the exact same pattern, right? This looks like pattern that that was obtained before, right? So notice you have a blue flat line. It should have been really flat, but as you can see, they don't come out exactly flat. It's a little curvy, but this one definitely, you can see it's a curve, right? And you can see the different phase values right here. Let me go back a little bit. So, oops. And so where do you play? So right here you can set out the different phase values, right? So this is like moving the waves back and forth, right? A little bit. And you obtain that way two different patterns, right? All right, let's go to an extension of that experiment, and this one is the one that has puzzled physicists for so long. This is the delayed choice quantum erasure experiment. I put there Schully because Mariam Schully was a person that conceived it theoretically. Some other people did the experiment. I'll certainly show you the citation for that work. So let's take a look. So here's the diagram for that one. So number one, pump light goes through two slits. Twin photons emerge from A, and B. Well, I kind of got stuck there. All right. Twin photons emerge from A and B. One of each goes in two different directions, the upper and the lower, right? So right here, we're starting to pump photons, and as you can see, you got A and you got B. And as you can see, let me try to make this one a little bigger. And as you can see right here, you create two twins, two sets of twins, right? You see a total of 4 right there. Okay, so now I'm not going to pretend that I understand what goes on here. I can tell you that what comes in through these two slits goes into these two crystals, and these two crystals split once in a while one of the photons into 2 photons. Okay, you can imagine like it breaks it apart, but that's not exactly correct, but that's just a simple way of thinking about it. All right, number 2, photons from A or B go to D0, the upper part, and photons from A and B also go to D1 or D2 in the lower part. In contrast, D3 takes only photons from A, right? So as you can see, right here, these 2 photons here end up in D0 right there, and these 2 photons here sort of go into different detectors here, right? You can go into 1, you can go into D2, and you can go into D3. Now D3, notice D3 only gets information from A, right? Now the other 2 get information from both, and you don't know which path. Okay, so that's important, right? So you can think of this one. This one tells you which path the information is following. These 2 detectors here don't tell you which path the information is coming. So you can imagine, you can think of this one as a wave. We're going to obtain some kind of wave behavior here, and we're going to obtain some particle behavior here, and everything in quotation marks, right? Because we're speaking very loosely here. All right, and then 3, D0 can move along the x direction, right? So how are we going to change the phase value? Well, we're going to move this one right here into different directions, and you might be wondering, well, what does that have to do with the other ones? Well, let's go to the method of collecting data for this experiment. All right, what was the method of data collection in the delayed choice quantum erasure experiment? joint count rates between D0 and D3 for different x values were measured and plotted. Okay, so we're measuring, notice, joint count rate. We're not measuring the count rate in just one detector. We're measuring in two detectors, right? Joint count rate, right? What is the coincidence rate into two detectors, right? Joint count rate between D0 and D2 for different x values were measured and plotted. Also, joint count rates between D0 and D1 for different x values were measured and plotted. Right? So as you can see, all of them were measured together with D0. So that's the only one that they have in common. So as we move D0 along the x direction, we're supposed to get some a pattern that varies depending on which of these three we're measuring. Okay, so let's take a look at the data. Okay, so here's a cartoon of the data. Let me put myself up here. So results from the delayed choice quantum eraser experiment. So along the horizontal axis we have the x position of D0, and the vertical axis shows you the count rate intensity, right? So now look at the labels. So for D0 and D1 we get a wave pattern. You can see it right there very clearly. For D0 and D2 we obtain a wave pattern, and as I mentioned earlier, as I suggested, here's a particle pattern, right? It's not flat, it's more like sand falling into this area, and some goes this way and some goes this way, right? But that's particle behavior right there. Notice that there is another one right here that it's supplied because it was not measured, but a fourth another detector could have been added, a detector D4, and we could have obtained another one just like this one right here. So okay, so remember, this is when we know which path the information went through. So this one is telling us that the information came from A only, right? But when the information comes from both, and we don't know which way it is, which one really it is going, then the information interferes, and then you get a wave pattern, right? Okay, so what? You might be wondering what's going on here. Well, all right, things to notice in the results for the delayed choice quantum eraser experiment. Well, okay, particle behavior is observed in joint measurements of D0 and D3 for all x positions of D0, right? So I mentioned that. Wave behavior is observed in joint measurements of D0 and D1 for all x positions of D0, right? Mentioned that. And wave behavior is observed in joint measurements of D0 and D2 for all x positions of D0, right? Mentioned that. So what about time? Okay, this is where it starts getting interesting, because remember, the point of delayed choice experiments is to show that the past of a system can be changed, the history of a system can be changed in the future, right? And notice that a measurement of D0 occurs before measurements of D3 when joint measurements of D0 and D3 are detected. Okay, now let me go back a little bit. Okay, so let me go back to the setup, and I should mention something right at this point. Notice that the paths are not the same length, right? The path to go from A, B into D0, D3, D1, or D2 is not the same, right? Now, the shortest path is to D0, right? but it takes longer for the information to go into D3 or to go into D2 and D1, right? Okay, so that tells you that information doesn't arrive at the same time, right? So each detector is measuring the information at different times. So let me go back to time here. So measurements in D0 occur before measurements in D3 when joint measurements of D0 and 3 are detected, right? So yeah, they don't occur at the same time because the paths are different. Measurements in D0 occur before measurements in D1 when joint measurements of D0 and D1 are detected. Okay, right? And also measurements of D0 occur before measurements of D2 when joint measurements of D0 and D2 are detected, right? Okay. Now, what conclusions can we make out of this experiment? Why is this puzzling? Well, let's take a look at it. Number one, two patterns of joint count rates are obtained, one for a particle pattern and one for a wave pattern, even when both share the same D0 detector, right? Okay, so two different patterns, just like Wheeler's delayed choice experiment, we get two different patterns, right? Okay. So now for what else? The joint count rates for the wave pattern requires a longer time after measurements of D0 are done than the joint count rates for the particle pattern after measurements of D0 are done. Right? So this one is slightly different. So the wave pattern required, you can say, extra time after the measurement of D0 was measured, right? So that kind of gives you the impression that, I'm going to go into 3 now, because 1 and 2 above, it is said that the measurements in D1 and D2 erase pattern obtained with D3 and D0 for all x positions, right? So it almost looks like, let me go back here. It almost looks, this is what, oops, almost looks like this pattern and this pattern erased this pattern right here, right? It kind of makes you think that this one happened, but then later this one happened, right? That's just perception, okay? I'll explain, that's just metaphorical, I think. The word erase is just the way it looks, right? It looks like this one erase this one, right? But it's not telling you anything about retrocausation. So here it is, okay? Is a delayed choice counter eraser an example of retrocausation? Not necessarily, right? So it's not necessary to start explaining things in terms of back in time causation, like a future event can cause something in the past. Okay, let me explain this part here. No need for retrocausal explanations because count rate patterns obtained were done by different joint measurements with only one detector in common, D0. So in other words, two different, remember, the patterns that were obtained with two different detectors, right? And so of course, you use two different detectors, you get two different patterns, right? So, there's no need to be referring to back in time causation for the patterns, right? They were not measured at the same time, but that doesn't mean that the act of measuring one sent information into the other measuring device and erase it, right? Because we are using different detectors. Okay, and joint count rate between two detectors does not entail necessarily a causal connection between the measurement themselves. So when you're using two detectors and you're measuring the coincidence rate, you're just measuring how often they happen together. That does not have to do anything with causation, right? Okay, so two ways to look at why retrocausation is not necessary, right, to explain the phenomenon. There are some that will interpret the phenomenon as, happening back in time. All right, well, be my guest to use whatever interpretation you want, but it's not necessary to go that far. I think it's simpler to just think, you're basically measuring joint rates and with different devices at different times. Okay, and if you want to know more about retrocausation, I suggest you read this wonderful philosopher, physicist, mathematician. So, retrocausation and the delayed choice quantum erasure experiment. A common fallacy in quantum mechanics, why delayed choice experiments do not imply retrocausality. So you can actually check it out. Okay, just type it in Google and it will come out. Okay, I cite David Ellerman in my paper because it's the one that sort of explains that part really well, and I think my experiment with the IBM quantum computer sort of shows that as well, right? Okay. So let me go into now my little experiment. So a quantum computer version of the delayed choice quantum erasure experiment, part 1. Okay, so I did it in 2 parts. I added some extra stuff. Okay. All right, so here's a circuit that I used for the experiment. So let me begin here. A measurement of Q0 in the Z basis are analogous to measurement in D0, right? So this one right here is analogous to D0. Measurements of Q1 in the Z basis are analogous to measurements of D3, right? So right here, this one, it's analogous to D3, okay? Measurement of Q0 in the Z basis are analogous to measurements of D1 and D0, right? So right on the bottom, right here, this one right here, this one right here is analogous to D1 or D2. Okay, as you can see, there are some extra qubits right here, which play another role. And then it says here, all U1 gate phase values were varied manually in the range 0 radians to 2 pi radians. So these gates here, U1 here, U1 here, the phase value was varied manually, just like it was done for the quantum computer version of Wheeler's delayed choice experiment. Okay. All right, and I put her here in red because this is important. Number 1, measurements were automatically done in order after compiling the program. That is, Q0 was measured first and Q4 was measured last in every run of the experiments, right? So this is actually, you can actually see when you compile the program that these measuring devices are done in order, right? So first this one gets measured, then this one, and it goes all the way down. Okay, oops. Oh, wow, what did I do? Okay. Okay, wow. Okay. All right, there you go. Okay, so yeah, so measurements are done in order, right? And then another point is that qubit 4 requires the output from Q0 and requires extra processing gates to measure it. That is, the output of Q0 was processed faster than the output of Q4 in every program run. So notice that this one here requires less processing time than this one right here. Okay, so in other words, you can kind of think that D1 requires less time than D4, right? How do I know that? Because as you can see, the information from this one has to go down, and and then get into this one right here, and then on top of that, it has to needs the information with all the other qubits in order to be processed. As you can see, this one requires less processing time, right? And that's going to be important in order to come up with conclusions about time. Okay, note, the uncertainty measurements is not known. I put it nice and big right there because, right, you know, I don't know, the measurements were measured in order, but by the program. But if the uncertainty is large, well, that doesn't necessarily mean that all measurements were measured in order, right? Okay, so that's a big question mark in the experiment. All right, so let's understand the output because we're using a quantum computer. So the output for each run. The output was a computational basis element, which is a tensor product of the 5 qubits involved. So right here is kind of like the way the output looks. And C is kind of like the intensity. And here, and this is the way you see all the qubits were written like this. Okay. Anyway, so C, its absolute square represents the probability of the basis elements, right? Q4 and Q3, qubits associated with particle pattern. Okay. This one's right here will tell us about the particle pattern. Q2, when output is 0, a particle pattern is generated. When output is 1, a wave pattern is generated. So basically in the output, this one tells us what we're looking at, a wave pattern or a particle pattern. That's why I obtained extra qubits, something that you don't get in the lab version of the delayed choice quantum erasure experiment. And then Q1 and Q0, qubits associated with wave pattern. Okay. So the best way to understand this is just to look at the results, okay? The results speak by themselves. All right, so right here, okay? Notice, you can say this is a flat pattern right here. You can say this is a flat pattern right here. You can say this is a flat pattern, and you can say this is a flat pattern. And you can say this one is a wave pattern, right? Because, you know, it looks like like it's concave down, concave up, right? This one is concave down, and concave up, right? Okay, so as you can see, we obtain 2 different patterns as were expected, okay? And you can see the computational basis right here for each one, okay? You can see the computational basis for each one and for all of them. And of course, in the on the bottom, you can see the values for all of them. And on the vertical axis, you can see the intensity, just like the other experiments, right? So we obtain 2 different patterns. So now what? Hold on, kind of got stuck here. Okay, understanding the results. Number 1, the particle pattern results when there is no activation of the U1 gate on Q3, right? Okay. The wave pattern results when there is activation of the U1 gate on Q3. Okay, so let's go back to the program right here. So this one right here activates the upper part or the lower part, right? So this upper part, you can think of it very loosely as the one that gives you the particle behavior, and this part right here gives you the wave behavior right here. So that's what that's talking about. Okay, so number 3, the particle pattern information is required to obtain the wave pattern. Right, so let's go back to that one. Right, so notice, as I mentioned at the beginning, this information here is required in order to process this information right here. Okay. Okay, number 4, because 1, 2, and 3, the wave pattern requires longer processing time than the particle pattern. Okay, so that's an interesting conclusion. Okay, kind of like what happens in the delayed choice quantum eraser experiment in the lab, right? The wave pattern kind of took longer to be formed after measurement of D0, right? And number 5, because of 4, the fact that Q0 and Q1 were measured before any other qubits at the end of every run of the experiment, we can say that those other qubits erase the particle pattern. So we can use the same language here, right? You can say that in the data that we obtain, you can say, you can say that this pattern erase this one right here. You can say that this one erase this one right here. Okay, this one erase that one. This one erase that one. Why is that? Well, because it looks that way, right? Is it really a result of causation? No. Okay, but I'll get into that. Now, I did a second part to this experiment. Okay. All right, so this is part 2. Okay, and just like the other experiment settings, but there's a little difference, as you can see. Okay, notice that I don't have a measuring detector right in this part, and I just have a measuring detector in the first one. Okay, and you might wonder, well, why did I do that? Okay, well, let's take a look at it. Well, the reason I did that is just to obtain a nice wave pattern. Okay, as you can see, I obtained one wave pattern this way and another wave pattern going this way, and I got a double because why did I get a double? Because if you move myself up, so I added another one here, another measuring detector. Okay, and well, and you still might be wondering, well, what's the point of that? Well, here comes this is the interesting part. Okay, now by removing measuring device from Q0 and setting it in Q1, the wave pattern disappears. Oh, so I just move the device from here to here, and guess what? Now the wave pattern disappears. Okay, so in a way, you can think that the wave pattern, this wave pattern here, here, is the result of Q0, right? The result of Q0. Okay, well, you can, let's put it like this, you can interpret that what is becoming a wave is Q0, right? Okay, it's one interpretation of the information. Okay, there are many interpretations you can make out of the information, right? But certainly we can make that information, that interpretation, sorry. And notice that if you just measure Q0 alone, well, you just get a flat line. Okay, and something that was not done in the delayed choice quantum eraser experiment in the lab, right? You don't see in the paper. If you look at the paper, you'll see that there's no data for just detector D0 alone. Right? It's always joint measurements. So it kind of makes you wonder, well, what happens if you just measure D0 alone? Well, I did that here, and as you can see, I just get a flat line, and I don't get a flat line when I measure with the other ones, right? But if I remove Q0, then the wave pattern disappears, right? So I'd be saying, well, what's going on here? Okay. So what does part 2 of the computerized version of the delayed-choice quantum erasure experiment show? Okay. Number 1, measurements on Q0 is necessary to detect a wave pattern, but it's not sufficient. Okay. Number 2, measurements on Q1, Q2, Q3, and Q4 are necessary to detect a wave pattern, but are not sufficient. Right? 3, from 1 and 2 follows that there is the choice of saying that the wave pattern is a result of Q0 when the other qubits are considered detecting qubits, or that the wave pattern is a result of the other qubits when Q0 is considered a detecting qubit. So right here you have, you can consider one qubit to be the detector and the other one observed, or you can do it the other way. One is the detector and the other one is the observed. Right? You can reverse the roles. So there is a relational interpretation that you can make out of the results. Conclusion. Number 1, the wave or particle behavior could be associated with Q0 when the rest of the other qubits are considered detecting qubits, right? And I notice that I put in a different color that you can also say, and the same can be said about the other qubits when Q0 is considered a detecting qubit, okay? Number 2, measurements on the seed basis on qubit Q0 alone without the other measuring devices in the other qubit does not produce a wave pattern, right? Okay. And 3, we have a choice of saying that the measurements of Q0 with Q3 and Q4, which originate the wave pattern, erase the measurements of Q0 with Q1, which originate the particle behavior, or that measurements of Q0 with Q1, which originate the particle pattern, define measurements of Q0 with Q3 and Q4, which originate the wave pattern, right? So, okay, so we have a relational interpretation that we can make of this experiment, right? 4, there is no need for causation, retrocausation to be specific, from one measuring device into the other measuring device because A, the probability percent were the result of joint measurements with several measuring devices, and B, 2, the wave and particle patterns were formed by superposition of phase differences or not on qubits other than Q0, right? Okay, so you can see right here in this experiment more clearly, I think that how it's not a result of retrocausation, right? And if you look at the circuit, well, any circuit here, you can see that the way this is what is forming a wave pattern right here, not this one right here. Okay, so it is when you do joint measurements of the upper qubits with the lower qubits, you end up getting a wave pattern. Okay, and Q0 is necessary in order to do that. You remove it, you don't detect a wave pattern. So it's the result of joint measurements that gives you a wave pattern, and it kind of makes you think that the wave pattern is happening here, right? Okay, but you can think that the wave pattern is also formed right here. Okay, all right. So let's move on. And let's move on to the comparison of one with the other. Well, I don't know where to put myself, okay? Computerized version of delayed-choice quantum erasure experiment with versus laboratory one, okay? So the computerized version, the uncertainty in time measurements is unknown. So remember here, we don't know exactly how long it takes to do the measurements. You know, is it done quickly compared to the time of processing, or not? We don't know, right? So it, it could be that some measurements were in fact measured before other measurements, but if the uncertainty in time is huge, there's some overlapping, so we don't know, right? So that's one advantage for the laboratory version. Uncertainty in time can be easily measured, right? But the computerized version of the delayed choice quantum erasure experiment can be repeated easily. And for the laboratory version, one must have access to the equipment and set it up. Right? It's a little more difficult to recreate that experiment at home, right? The computerized version, you can actually take your device and just do it. Okay, non-joint measurements can be easily performed and were presented. And here, for some reason, more data was not presented, such as non-joint measurements, right? So this is referring to the fact that you can actually measure D0 by itself, right? If for some reason they didn't measure, the data with D0 alone, just comparison. And the theoretically, the experimental setup is correct. So you may say, well, the uncertainty in time is not known, but you can say theoretically, this is the experiment that the experimental equivalent of the quantum computer that gets the results. And of course, over time, when as quantum computers improve, maybe we'll have a way to measure the uncertainties, or we'll know for sure, what's the uncertainty right there in the uncertainty in the measurements. Theoretically, now for the laboratory version, theoretically the experimental setup is correct. Of course, it is correct. Okay. Well, okay. Hope you enjoy this paper. You can download it again, different repositories. You can actually read all the calculations, and of course there's much more difficult math to follow. Okay, if you enjoy mathematics, you certainly will enjoy all the math that I introduced in the paper. Okay, well, I'll see you next time, and for those about to quantum, we salute you. Have a great one.